All right, so welcome to Lab 5. We're going to play around with discrete probability distributions. And if you recall, a probability distribution is just a relative frequency histogram. We're going to generate one by playing with some dice. And so the game we have here is available on our course website under Labs, Discrete Distribution. I'm going to play around with both empirical and theoretical probabilities and practice finding the mean, the expected value of a probability distribution or a relative frequency histogram. Here, the procedure is to bet on an object. By an object here, we mean a die that we're going to roll. So we have this six-sided die that we can roll, and we're going to get a number between 1 and 6 inclusive. So we could get 1, we could get 6, 2, 3, 4, 5 in between. The way this game works is we are going to have 3 dice, and before we roll them, we're going to pick a number that we're interested in. So I'm going to pick the number 5 and I'm going to roll, and I'm hoping to get a match. Okay, so I have one match. Possibilities are I get no matches, no 5s here. Too bad my number's not 3. I got 2 5s there. That's a pretty good deal. So I could get 0, 1, 2, or 3 5s, and I'm hoping to get a 5. So I would wager $1. And then I'm going to get some payback based on that. To the left. Now, again, we're going to pick a number and we're going to count the number of matches that we get. The number of matches will decide the profit. For example, it could be our profit's -1 for no matches. That means I paid $1 and I lost it and I'm done. It could be the profit is $1 for one match. So I'm hoping for a 5, 1 5 shows up. Now, if I paid $1, they would have to give me a payout of 2 for me to have a profit of 1. I'll go over that again in just a minute. So here's one possible profit scheme. -1 for no matches, profit of $1 for one match, profit of $2 for 2 matches, and a profit of $3 for 3 matches. What's the theoretical probability of one die matching? Well, since there are 6 different numbers available on the dice, a single die has a 1 in 6 chance of giving me the number I want. We're going to play around with what's the possibility of getting 1, 2, or 3 or no matches on the die. And we'll do that in a couple of different ways. So we're going to choose an object, a number to bet on, and we're going to roll the 3 lucky dice. We're going to count the number of matches each time. We're going to repeat this procedure many times. Now, alternatively, we could randomly generate the die rolls. And there's instructions down here about doing that at the end of the lab. I'll get to that in a minute. X is going to represent the number of matches that we see. So was there 0, 1, 2, or 3 matches? Those are all the possibilities. I don't know what's going to happen each time, so it varies, and it's random because the die results are random. So X is a random variable. It's a type of random variable called a binomial, and binomial randomness has 2 parts to it, which we'll get to in a minute. Then we'll have another random variable called Y. That's the profit that we end up with per game. The game is rolling 3 dice. And so we're going to roll the die a bunch of times, and we're going to fill out this frequency table. So we're going to count up after we do it many times, how many times we had no matches, how many times we had 1 match, or 2 matches, or 3. We're going to calculate the relative frequencies based on that, and then we're going to do some more calculations for those. All right. So here, I broke my page. Let me fix it. There it goes. All right, so let's take a look. Again, I am going to roll my dice, and let's say that's my roll. I was hoping for a 5. I got 2 matches. So as far as my spreadsheet goes, I just want to kind of keep track of that. So I'm just going to write matches here. And I got 2 matches on my first try, and then I just keep doing this. Again, no matches. And so I'll make a note that I have no matches on that trial. You keep playing this game over and over again. Now, if you have dice at home, you can roll real dice, so you might have a match. Now, how many times do we have to do this? That's a good question. A lot. No matches. So in the lab today in class, we did this, and as we were going through it, we have X, which is the number of matches. We have 0, 1, 2, 3 matches. And then we are going to find the frequency as we play. You'll need to come up with some, oops, hold that right. You'll have to come up with some rolls of your own. You can do that 2 ways. 1, roll real dice. 2, go to a place like random.org and roll 3 of their dice and see what happens. 3, we can use a random number generator on a spreadsheet, which I'll show next. Let's just suppose, for example, we rolled a whole bunch of times and ended up maybe with something like 76 zeros and 5. 1, matches of 1, and maybe we ended up with 10 times we found 2 matches, and maybe 1 time we found 3. So if I sum those results up, that means I must have played the game 142 times. Finding the relative frequency, we want to take each frequency and divide by total. So the relative frequency here would be about 53.5. The frequency here, this number divided by this number, and so on. See it. So here are my relative frequencies. Some of the relative frequencies should add up to, correct, 100%. We could write those as percents if it makes us feel better. So again, I just made these numbers up. They do not reflect an actual bunch of trials of this experiment. So again, 1 trial of this experiment is rolling 3 dice and seeing what happens. And my claim is this is what's known as a binomial distribution. To have a binomial or binomial probability. Will I get today? Have a binomial probability, you have to meet a few conditions. 1, each trial must result in either a success or a failure. Someone pointed out in class the other day, soccer wouldn't work here because it could tie. The probability of a success must remain constant. So for example, success here is me rolling a 5. Probability of rolling a 5 is 1/6. It's always 1/6. And then each trial must be independent. Have those conditions and have a binomial probability. There's a formula for binomial probabilities. We're going to figure out what's the formula, and then we're going to figure it out by making a chart for it. All right, so the other way, besides rolling the dice to do this, is remember spreadsheets have a rand between function. And so I could say, please give me a random number between 1 and 6. And so that simulates rolling a die. Now I have 3 different dice. So if I fill that across twice, here's the result of playing the game once. Now move those over. something here. So let's say this is die 1, this is the result of die 2, and this is the result of die 3. Now I am hoping to get, let's say, a 5. And every time I do something on the spreadsheet, it re-randomizes, so that takes a little getting used to. And so I'd like to see a 5 here. Now I can easily look and see that as far as matches go, there are 0 matches there, but now there's 1 match. That's effectively why it changes. Not the problem. There is a way to have the computer look at those 3 cells and say, are there any 5s there? And that is what's called a count if. A count if works. You give it some stuff to look at. So look at these cells right there. I want you to count them if, comma, they result in this case, a 5. Close parentheses, and it will tell me how many 5s there are there. So now what I have in this particular row, I have a formula that gives me a random dice result, and I have another formula that looks at these 3 and tells me if there's any 5s there and how many there are. So now I can take these suckers and I can fill them down a bunch of times. Now maybe I just fill them down 10 times there. And so here I just did 10 trials of the experiment, and these particular trials lead to either 1s or 0s. Now, there are theoretical probabilities for this, but remember there's what's called the law of large numbers, and the law of large numbers says empirical probabilities will approach theoretical probabilities as you do more and more samples. So 10 ain't enough, 50 probably ain't enough. We'll probably need something like 1,000. Maybe a couple hundred will work. So I'm just going to fill this down a ways and see what happens. So filling this down further. And let's suppose I'll do 100. So I just drag it down and let it go for a little ways. Now I'm going to have to go to row 102 because my first 2 rows were occupied by other stuff. So we can look back through here and see that they're mostly 0s and 1s. 2s appear once in a while, but mostly 0s and 1s. And so there's got to be a reason that I'm getting 0s and 1s mostly, not many 2s, and I don't see any 3s yet. Let's tighten this up a little bit. Next thing I want to do is I want to make a frequency histogram on this, and we've done that plenty of times before. Now here, instead of calling them bins, I'm going to call them my x values. My x values are either 0, 1, 2, or 3. And what I want to do is I want to find the frequency of these x values. To do that, I use the frequency command. Before I use the frequency command, we need to highlight the cells. Always one cell more than the data. It's frequency. I want to find frequency of the numbers in this column. It'll ignore the word matches, empty space. And I want to use these as my bins here. Close parentheses, and it will do my counting for me. And when I do my sum, I should find that this adds up to 100 trials, 3 dice at a time. Relative frequency. Another name for relative frequency, you guessed it, probability. So again, every time I type something, it's going to change these because the random numbers. It's going to deal with that. So here to get the frequency, I don't want to type 59, I want to click on it. And I'm going to divide by 100, which is first for the moment. And I can put that formula down a few times, and I can get those probabilities. If I sum those probabilities, if this is really a frequency histogram or a probability distribution, then they should add up to 100% or 1. Okay. So what I've calculated here is a probability distribution, which represents this column and this column right here. To find the mean of a probability distribution, we went over this in class, I have to multiply each outcome, 0, 1, 2, or 3, by its probability and then add those up. That's a formula called sum product. So I want to find the mean of this distribution. Equals sum product of my x's times my probabilities separated by a comma. And so here I find the mean is about 0.5. Now, the mean we often refer to of a sample as x with a bar over it. Now, x bar is an x value. Okay, so what the hell does it mean here? Well, x represents the number of matches, right? So x bar means the average number of matches I expect to find if I play this game a bunch of times. And so what we're finding is we're going to get about half a match. What does that mean to have half a match? I mean, either you matched one dice or you didn't, or you matched two or you matched three. So since this isn't a whole number, that means I have to look at the two whole numbers around it. So my interpretation of this for my mother would be something like, on average, I expect to match 0 or 1 die. I don't expect to get 2 very often. I don't expect to get 3. I will mostly see 0s and 1s. That's what this is telling me up there. On average, I expect to get a match 0 or 1 on 0 or 1 die out of the 3. All right. Next, we need to take. So that's one version of the experimental and empirical probabilities. And I did this experiment a few times. So here I did it with 1,000 randomly generated groups of 3, and I get a similar distribution to before. Here I find I get about 57.9% compared to the 65% I got there. A little different. 35% roughly for one match, 25% here. So every sample is going to be a little bit different. I look back at this one. The first time I did the experiment, I did a random sample of 50, and there I found probabilities of 54, 42, and 4. And then I did a few more. There's another sample of 50, probabilities are 60%, 34, 6%, 0%. And so each one is just going to be a little bit different. What I would like to find are the theoretical probabilities. So we're going to take a shot at that next. So I'll guide you through that. Let's go back to the other sheet. Easiest situation to look at would be finding 3 matches. So as far as that goes, the probability of getting the first dice to match is 1 out of 6. Probability of getting the second dice to match, well, they're independent, that's still 1 out of 6. And the probability of getting the third die to match, that's still 1 out of 6. Now, I want the first one and the second one and the third one to match. Since they're connected by and, also each die roll is independent of the other, I can multiply those 3 together. So if I multiply 1/6 by 1/6 by 1/6, that's going to be 1 times 1 times 1 divided by 6 times 6 times 6. And so I'm going to end up with a probability of about almost 5%. Oh, sorry, 0.5%, a half a percent. Right, so let's turn these into percentages just to check that out. So I get about a 16% chance of 1 match. If I want 3 matches, that means I have roughly 16% times 16% times 16%. And that gives me about a half a percent, a 0.46% chance. Right? That's a probability of 1 out of 216. So there's that same percentage as a decimal there. So that's 3 matches. Skip 2 and 1. Let's go down to 0 matches. As far as 0 matches go, there's 5 ways I won't match. I'm hoping for a 5, but if a 1, 2, 3, 4, or 6 shows up, I lose. So the probability that I get no match is 5, 6. First dice, 5, 6 on the second dice, and so on. Let's see, just pull that over. Beautiful. If I multiply those together, I get 5 times 5 times 5, which is 25, divided by 6 times 6 times 6. So that's going to be equal to 5 times 5 times 5 is 125, divided by 216, which is 6 times 6 times 6. So the probability I get no match is about 57%. All right, so what about 1 match and 2 match? So here's the way I look at those. Write it down here and then bring it up there. So as far as 1 match goes, it's possible I get a match and then no match by no match. I could also have no match, then a match, then no match. So basically there's 3 different places the matching number could occur. So I could also have no match, no match, match. Now, as far as the probability of that goes, let's put this first one here. Probability of a match is 1 out of 6. Probability of no match is 5 out of 6. And the probability of another no match is 5 out of 6. Multiplying those guys together gives me the probability that I have a match followed by no match followed by no match. Now, the bottom line, these other ones are pretty similar. It's just the order of the multiplication is different. Now, you can multiply in any order you want and still get the same product. So basically, when I multiply those 3 numbers together, let's do it off to the side here, I'm going to have 1/6 times 5/6 times 5/6, and that's going to give me about an 11% probability. Turns out this has about an 11% probability, and so does that, because it's just different orders of these 3 numbers multiplied out. So that means ultimately the probability of getting only 1 match, because the match could occur in 3 different places, is 3 times the probability over there. So 3 times 1/6 times 5/6 times 5/6. So I get a probability of about 34.7%, which is 3 times the probability of any one of these guys. Now, 2 matches, so again, that's 1 match. And you can draw this in a tree to see the same thing. I challenge you to do that. 2 matches. That would be something like match, match, not. Match, not match. Or not match, match. And it's similar to the above, except the probabilities are slightly different. So here, it's going to be something like a match is 1/6. Another match is also 1/6. And not match is 5/6. So that's about 2% probability of getting any one of these guys. Since there's 3 ways that can happen, my answer is going to be 3 times that. So my claim is that 2 matches comes from having 1/6 times 1/6 times no 5/6, no matches. And there's 3 different ways that can happen, so my answer is going to be 3 times this times this times that. Alright, so good total full of shit. Let's double check some of this. So there's only 4 possibilities here. No matches, 1 match, 2 matches, or 3 matches. Those are the only ways this game can come out. I believe that these are the 4 possible probabilities that go with those. If I have all possible events, and and those events are simple, then they must sum to 1. So let's just take the sum of those probabilities and see what we get. It's 100%. Now, that doesn't guarantee that I'm right, but that's one set of arguments for my method. There's another argument you can use by drawing a tree. We did one in class last week. We'll do more next week. So it could make sense later. This didn't quite make sense yet. So again, what I've calculated here are the theoretical probabilities. Another way to come up with those theoretical probabilities are what's the binomial formula. Most spreadsheets have a binomial formula. You can start with binom. In Google Sheets, it's binom dist. In Excel, it's binom dot dist. And so I bring up that formula, and then that formula is going to ask me for some information. So it says, what's the number of successes? Well, the number of successes is the number of matches that I find. And then it's going to ask for the number of trials. Well, the number of trials is how many dice are rolling. I'm rolling 3 dice. And the probability of success here is the probability of success on any one of those. Cumulative means, do we add up everything below that? We'll get to more of that later. We're not here. So in this particular case, let's see, I'm on the line with 3 matches. So I want to know, what's the probability of getting 3 matches when I roll 3 dice, and each dice has 6 sides, so the probability is 1/6. And I don't want to accumulate these, so I hit false. And there's my same matching probability. This one here is similar. Finding dist. Here I'm hoping for 2 matches. I'll roll in 3 dice. Each die has a probability of 1/6 of giving me a match, and again, false. I'm not accumulating. And so there's my 6.9% roughly. I just keep calculating this. Binomial this, so it's going to calculate a binomial probability. And again, binomial probability is when I have a situation that results in a success or a failure. Probability of a success is always the same, 1/6 there, and each event is independent. So back to this here. That's up. So here I'm hoping to see 1 match, 3 dice, where the probability of success is 1/6. On a computer, you can tell it to do false by entering the number 0. 34.7%. Finally, the binomial probability for no matches on 3 dice, probability of success is 1/6. I get those exact same probabilities. So once we know a situation is binomial, we don't have to reason through the ways something can happen. The formula does that for us. We just have to establish that we're sure we have a binomial situation. Okay. So I'm going to clean this up a little bit. Let's cut these cells out. So just delete those and move these suckers over. Let's get rid of this stuff. So next thing I want to do is I want to double check. Let's call that 3, 2, 1, 0. I want to double check the expected value here. What do I expect that to happen? The empirical results said I should expect to have between 0 and 1 matches each time. And to find the mean of a relative frequency histogram, which is also a probability distribution, we multiply these two numbers together, 3 times its probability, 2 times its probability, 1 times its probability, 0 times its probability, and add them up. So that is what's called sum products on a spreadsheet. So I want to take this group of numbers, multiply them line by line by this group of numbers, and then add them together. And it says I have an expected value of 0.5. Now 0.5 is the average X value here. X value means the number of matches. And So I find that the number of matches is a half. I can't have half a match. That must mean I get 0 or 1 match. All right, so another thing that we need to calculate is standard deviation. Standard deviation is a little tricky. The procedure before to do that was to find the deviations and then square them. Deviation is how far one is from the mean. So to calculate that, I take the number 3 and I subtract the mean, 0.5. That's the deviation of 3. I then want to close the parentheses and square it. Now, and let's see, it's not supposed to be a percentage. Turn that off. It doesn't want to turn off. Let's go to here and make it automatic. There we go. When I fill this formula down, it's going to change the 3 to a 2, which is good, but it's going to take the 0.5 and then look down here for it. That's bad. So I need to fix the mean in row 7 by making a dollar sign on 7, and then I can fill the squared deviations down. The reason I'm calculating those is I need those to find the expected value. The standard deviation. Standard deviation, if you recall, to find it, we find the deviations, we square them, and we add them up. And then we divide by how many. Now here, I don't have how many, but I have percentages. So the trick here is what we want to do is we want to sum the x values, the probabilities, times the deviations squared. Shortcut formula. That gives me what we call variance. To change variance in the standard deviation, I then take the square root of that. So I'll do this in 2 steps. So the standard deviation, I want to know what is the square root of the sum product of my deviation squares multiplied line by line and then added up with their probabilities. So I get a standard deviation of about 0.64. So on average, the number of matches I can get are about 6/10 of a match from the center, which is half a match. Sounds kind of weird. For this particular situation, we really don't need the standard deviation, but there will be some situations where we do need the standard deviation. And if that formula seems weird and wacky, we will go over it again and again. So you'll see it a few more times. There's some other shortcuts that we can use later. But the big thing I need to know here is that this situation is a binomial probability because it meets these conditions here. That means I can use the binomial formula to calculate any one of the probabilities. If I have a table that has some x values from a random variable and their associated probabilities, I can use the sum product formula to find the average value. Average value is also called the expected value. What I expect to have happen if I play this a bunch of times. So the expected value of matches is half a match. Standard deviation's a little tricky, we won't worry about that too much. All right, let's take another look at the lab. So I've helped set up a lot of it. One thing you'll need to do is make a decision on what you want your profit to be. You could go along with my recommendation here, or you could experiment with some other ones. So far, what we've set up here, I've set up here as I've been playing, is the empirical data, relative frequency. I've done, let's see, this calculation. We haven't done the sample mean for y. We haven't written that down. I've got an example of that. I expect you to draw, either with a computer or by hand, a histogram based on your relative frequency table, which we have calculated here in sheet 2. So here's one version. This one was based on 100 samples. Let's see. Some other questions you're going to try and answer here. theoretical distribution, we just set up using the binomial formula. You can fill in the y's and do some more work on that in a moment. And again, we want to make a picture of the probability histogram from columns 1 and 3 here. You can do that on the computer or by hand, and you have some questions to answer. There's a few other probability play type questions you're going to give a try at. There's some other discussion questions that you'll mess around with. We'll talk about some of these in class later. And then here's some instructions that I already went over for how to use rand between and how to use count if. All right, let's take a look at the profit, and then I'm going to shut up and let you guys play. So, I'm going to work off the theoretical distribution here. So I'm going to copy this information over to a new sheet. So I have my x values here. I'm going to move the probabilities over a touch. And I'll put the y values here. So I was thinking, these are kind of in the wrong order. Oh well, let's just go with it. That if you get no matches, then you've lost your dollar. If I need to put another column in here to explain profits, put a column called payout. So if you get no matches, you get no payouts, so you lost a dollar. Let's suppose that you get one match. The payout is $2. Since you spent a dollar playing the game, your profit is only $1. If you have two matches, let's say the payout is $3. Since you paid a dollar to play the game, that means you really only won $2. And similarly here, if you get three matches, let's say the payout is $4, that means you only made 3 because you had to pay a dollar to play. So I'm really interested in what is my profit. That's what y is. Payout happens, and I paid a dollar to play. So payout minus what I paid to play gives me my profit. So I don't need this column anymore. That's my explanation. To find the expected values of the y's, so the mean of the y's, which looks like of y's, there we go. I want to have a multiplication of the y times the probability. So I could do that by hand. I could calculate y times p. This guy, this guy. Repeat that for each row. And then I could add them up. And expected value, -0.7. I had to make this extra column to do that. The alternative to making that extra column, move this over to get it out of the way, would be to just use the sum product formula. And that's what the quickest way to get the mean of the probability distribution is. So the sum product, this column, times this column, you comment in between them, and then it's the exact same number with a little bit less work. What does it mean for the expected value to be -0.078? That means, again, this is the expected value of the y's. Y is profit, holding in dollars. So that means here I have an amount of dollars. So that means basically, if I play this game over the long run, on average, I'll end up losing about 8 cents. So no matter how many times I won, I'm going to lose enough that overall I'm not going to come out a winning man. Or over my lifetime, the casino is going to make 8 cents on me, 8 cents on my neighbor, and 8 cents on their neighbor. That's going to add up over time. So is this a fair game? The answer is no, because it's not a break even. But the casino wouldn't offer the game if it was fair. They need to have a slight edge. We could play around with, what would I have to make these numbers here so that it's not quite a bad deal for me? So I'll let you do that. All right, I'm going to shut up now. Let you guys play with this lab. If there's questions, call me, email me, text me, or I'll see you in class.